Welcome back to educator.com. Today we're going to talk about enols and enolates, which are components of aldehydes and ketones. So far what we've seen for aldehydes and ketones involve the reactivity of the carbonyl, the CO double bond. And the most significant part that we've seen so far is the polarity of the CO double bond due to the resonance, which makes this carbon partially positive and makes it an electrophile. In other words, nucleophiles add here. And that is certainly a significant reactivity of aldehydes and ketones and of any carbonyl. What we're going to shift toward in this lesson is looking at the alpha carbon, so that's the carbon right next to the carbonyl, and consider the protons that are attached to that carbon. It turns out that these protons, the alpha protons, are acidic. And what does it mean to be an acid? It means you donate a proton. In other words, they can be deprotonated. So in this lesson, we're going to explore the deprotonation of the alpha carbon and the consequences of that deprotonation. One other component that's of interest to us in this unit is the idea that any carbonyl-containing compound, like a ketone or an aldehyde, is in equilibrium with another form called an enol. Now this structure is called an enol because it has an alkene, a carbon-carbon double bond, and an alcohol, OH, and they're on the same carbon. The interconversion between a ketone and its enol form is known as a tautomerization. And as you can see, the equilibrium is favored in the reverse direction here. The ketone is more stable. Having that carbonyl there is preferable, so that's the form that it prefers to be. But what's important to recognize is that there's always a small amount present here of the enol, small amount present at equilibrium. So in other words, anytime you have a ketone or an aldehyde or any carbonyl-containing compound, you also have some of the enol form around. That's going to be important to us when developing some of the mechanisms down the road. So let's look first at this tautomerization mechanism. How do we go from a ketone to an enol? First, let's draw the enol form because that's going to be helpful for us to get from one place to the other. Let's think about where we're headed. And when we compare these two structures, we see that there's two things that need to be accomplished, and that's why we have a two-step mechanism here. Looks like we have an oxygen here, and now it's an OH. So one of my steps is I need to protonate here at this oxygen. I need to add a proton at some point. And here we have a CH3, and now it's a CH2, so I need to deprotonate down here. And of course, the pi bond is moved as well. That's going to be part of our mechanism and could be seen as resonance too. So the only question we have is those are our two steps. What step are we going to do first? Well, typically this tautomerization, the presence of enols, is going to be something we find in acidic conditions. So in acidic conditions, let's protonate first. So that's going to be our step one is protonate, and step two is going to be deprotonate. So I can protonate. Let's add in our lone pairs on this oxygen. Step one will be protonate the carbonyl oxygen. That's going to give an oxygen with 3 bonds and a lone pair, 1, 2, 3, 4, 5. That's a positively charged oxygen. Okay, and my second step then is going to be to deprotonate this alpha carbon. It turns out we're deprotonating right away. So instead of making a CH3, let's make this a CH2 so that we can see one of the hydrogens involved. And what we want to do is deprotonate that hydrogen. We can use the A- that we formed in this first step to be a base. And can you see how the mechanism might work to get us to our enol structure? Typically when we do a deprotonation, the electrons just go and sit on this atom, but instead of moving them here, we can move them over to be a pi bond, which would push this pi bond up onto the oxygen, and now we end up with the best resonance form here where we have no formal charges. So anytime we need to do a tautomerization, it's going to be a two-step mechanism, and we should practice this both forward and backwards until we get pretty good at it, so that it will be an automatic when it comes to part of a larger mechanism. Let's take a look at that reverse mechanism. We have an enol, and we want to go back to the ketone. This is now the more favorable mechanism that we'll see. And what do we have to do? Well, again, it's still going to be two steps. The reverse mechanism, I already have it written down here. The reverse mechanism is going to be the same number of steps, involve the same intermediates as the forward mechanism. And so what do we need to accomplish? Well, we have an OH that now needs to go back to an oxygen. So one thing I need to do is I need to deprotonate. Really helps to think about where you're headed and what you have to accomplish before you dive into a mechanism. And my CH2 becomes a CH3, so I'm going to protonate in this position. So those are going to be my two steps. And what do you think we should do first? Well, I'm thinking, again, because we're in acidic conditions, we should protonate first, so that should always be our first step in our tautomerization. So let's redraw this. I need to protonate at that CH2, so I can bring an acid over here, HA. And how could I protonate this carbon? Well, I can use this pi bond as my base. I can grab that proton, and that way I can add a proton to that position. And what happens to this carbon now? It only has 3 bonds, and so I have a positive charge. So just like anytime I protonate a pi bond like we saw for alkenes, you get a carbocation as your product. So our second step, that was step 1, was to protonate. Step 2 is going to be to deprotonate, so I can bring my A- in here to deprotonate this oxygen. And once again, rather than deprotonate and give an O- next to a C+, my mechanism would be much more efficient if I grabbed that proton and took these 2 electrons and filled them in as a pi bond between the carbon and the oxygen. And there we go, our 2 steps, and we've gone from our enol to our ketone. Now, I mentioned at the beginning that we're going to be able to deprotonate alpha carbons, and let's think about why a ketone's alpha protons would be acidic. As usual, anytime we want to determine something about the acidity of a compound, we should take a look at the conjugate base and see how stable that is. So here's an alpha proton. The pKa for such a proton is on the order of about 20. And if we imagine deprotonating it, so treating it with some strong base that can come in and remove it, we would get this carbanion. Now, normally a carbanion is not a very happy charge because carbon doesn't like having a negative charge, but there's something about this conjugate base that makes it reasonably stable. Well, that's because the lone pair is allylic. It's next to a pi bond. In fact, it's next to a carbonyl, which means it has resonance. I can delocalize this charge. Anytime I have an allylic lone pair, I can bring the pi bond in and bring this pi bond up, and I can draw a second resonance form. Anytime I could draw a second resonance form, that's always a good thing. And that explains why this is a reasonable place to deprotonate, because the conjugate base is resonance stabilized. It's a resonance stabilized carbanion. So it is a carbanion, but it is stabilized by resonance. And we can not only delocalize that charge, but we can delocalize that charge to the more electronegative oxygen. So this is an excellent resonance form. Now there's a name for this resonance stabilized carbanion. It's called an enolate. We just saw what an enol looks like. An enol has a double bond with an OH attached to that, right on that double bond. An enolate is the charged version of that structure. So we have a double bond with an O- attached to that same carbon. And so, as you can see, the title of this lesson is enols and enolates. So those are going to be the 2 species that we're going to be interested in both forming and reacting. It turns out we're going to be using both the enol and the enolate. If we have acid catalyzed mechanisms, that's when we'll be using the enol version of this compound. And in a base catalyzed mechanism is when we're going to be using the enolate version. So we'll see many examples of these in the following slides. Now, before we progress, though, I want to talk a little bit about deprotonating a carbon. That's not a very easy thing to do. We're going to see it repeatedly throughout this unit as a way that we can do it for alpha carbons. Let's think about other types of CHs. Okay, if you have an alkyne, that has a reasonable pK as well, somewhere around 25. That means that's a low enough number that if you do treat it with a strong base, it's possible to deprotonate here and form this carbanion. Remember, this is sp hybridized, and that's what made this possible, and that this is an okay carbanion to make. We've made these, we've used these in synthesis, and this is something that you should recognize as a stable carbanion. Okay, however, if you try to do that same thing with an alkane or an alkene, if you try to take an sp3 hybridized carbon or an sp2 hybridized carbon and try and do the same thing and react with a base, you would get a completely unstable carbanion here, completely unstable carbanion here. We cannot deprotonate alkanes and alkenes. Okay, it is possible to deprotonate alkynes, and the focus of this unit, of course, is deprotonating alpha carbons, such as aldehydes and ketones. Now, if we're going to be deprotonating, that means we need a base. Let's think about what bases are possible. If you had to name a base, you might say something like sodium hydroxide. We know that's a good base. So let's try that. Let's react this with sodium hydroxide and think about what product we would get. Okay, I could use hydroxide here as my base. It can grab this proton, and rather than have the electron sit right on carbon, most often when we deprotonate an enolate, we're going to go right to that better resonance form. So we're going to take these electrons and form a pi bond and move those electrons all the way up to be on that oxygen. That's the preferred resonance form. That's the better resonance form. So we can go ahead and draw the enolate that way. Okay, we could get that enolate. And what's the other product here? If I used hydroxide as my base, I just formed water. Now, water has a pK of about 16. So when we compare these two acids, the acid in the forward direction has a pK of 20. The acid in the reverse direction has a pK of 16, which is the stronger acid. Water is the stronger acid. And how does the equilibrium lie in a proton transfer reaction? It always lies in the direction of the weaker acid-base pair. So this reaction can happen, but just to a small extent. It's actually the reverse reaction that's favored in this case. So if I were to use a base like sodium hydroxide, what would happen is I would deprotonate just a small amount of this ketone. I would make a small amount of the enolate, small amount of enolate will be present at equilibrium. But for the most part, the ketone would still be a ketone. It would be the neutral form. And this is exactly the situation we want in certain reactions. So in those cases, we'll use sodium hydroxide. We also want to recognize, let's just make that note here, we have a large amount of the neutral ketone or aldehyde present at equilibrium. So with a weak base like hydroxide, we have mostly ketone with a tiny little bit of enolate around. If we wanted to completely deprotonate the ketone or aldehyde to make it an enolate 100%, we're going to need a much stronger base. And one of the bases that's been developed for this, that's used very widely, is this one. This is called lithium diisopropyl amide. That means we have an N-. Lithium diisopropyl amide is very conveniently abbreviated as LDA. And this is a great base because it is a very strong base and it is very bulky. Having those two isopropyl groups introduces a lot of steric hindrance. So that makes it a non-nucleophilic base. So in other words, LDA is just a base. All it does is find a proton to take, and that's its only purpose. So where do we have acidic protons? Of course, the alpha protons are acidic, so we can deprotonate here Again, we could show that mechanism. The N minus can come and be the base, and we could make this enolate. This would be the lithium enolate. It would be the lithium cation here because it's lithium disopropylamide. We most often don't have the counterion there, but of course it's there every time we have a negative charge. Okay, but the other product here now is going to be disopropylamine. Disopropylamine has a pK of around 40. This is a very, very weak acid. So that means this reverse reaction of having an enolate trying to deprotonate disopropylamine is very, very small, essentially non-existent. So we can think of this as a one-way street, as a way to completely deprotonate a ketone or aldehyde and convert it to its enolate form. Now, we don't always have to use LDA to do a deprotonation, a complete deprotonation. There are cases like this one known as an active methylene. An active methylene is when you have this situation where this carbon is between two carbonyls. So that makes it even more acidic. The pKa, let's compare it to this alpha carbon. This alpha carbon has just one carbonyl, so it's similar to an ordinary ketone. This has a pKa somewhere around 20. Okay, but when you put one next to two carbonyls, you have a pKa somewhere around 11. So it's orders of magnitude more acidic. And when you think about deprotonating anywhere else, neither of these are at all acidic, being next to an oxygen or just being a plain old alkyl. Remember, we're never going to deprotonate an ordinary alkyl hydrogen, so these are not acidic at all. So it's only the ones that are going to be alpha to carbonyls that we're going to be considered deprotonating in this unit. Sodium methoxide is a good base, so we could use that as our base. And if we did that, we would, let's just draw a line drawing here. We could deprotonate this completely. Again, the reverse reaction is minimal. We can completely deprotonate this alpha proton, and that's because this enolate not only has the carbanion, and we could delocalize it into this carbon on this oxygen on the left, the carbonyl on the left, but this could also have resonance to the other carbonyl. And that's what makes this conjugate base so very stable, and therefore makes the parent acid so acidic. Okay, my other product here, if I used ethoxide, gives me ethanol. That has a pK somewhere around 18. So again, comparing pK of 11 to pK of 18, that's a huge difference, and that strongly favors the forward direction and negates the reverse direction. So this is called a stabilized enolate. When we have something that's next to two carbonyls, that resulting enolate has extra resonance, and so we describe it as a stabilized enolate. So in this case, you could use LDA, but as usual, we always want to use a reagent that is the lowest reactivity, most stable, that makes it easier to handle and less expensive. And so sodium methoxide would work just as well here, so we would use that. Just a quick question. We talked about how sodium hydroxide is something that can be used to form a small amount of enolate. Why not use sodium hydroxide in this case? That certainly is on the order of the same basicity as ethoxide. So it would also do a good job of deprotonating this. But is there another reaction that can happen if I use sodium hydroxide as a base instead of sodium ethoxide? Well, take a look here. We have an ester in this starting material. So what would happen if you took this ester? There's another reaction that can happen besides just the acid-base reaction. We could also have hydroxide add into the carbonyl and then come back down and kick off the ethoxide. So we could also get hydrolysis, substitution, an acyl substitution here if we used hydroxide. So notice, because this is an ethyl ester, what base did we choose to use? We used the ethoxide. Okay, so the key here is for esters, when we go to choose a base and we want to deprotonate alpha to an ester carbonyl, we're going to use the matching base. So if we have an OR ester, we're going to use the alkoxide that matches that. So if it's a methyl ester, we use methoxide. Here we had an ethyl ester, we used ethoxide. And that's to avoid the reaction, the substitution reaction that can happen at the carbonyl. If you have ethoxide, ethoxide can add into this carbonyl, but what's it going to be kicking out? It's going to be replacing ethoxide, so that reaction becomes invisible and no longer a side product. Now, I just started to introduce how you could have esters be deprotonated at the alpha carbon, and that's true. We're focusing most of our reaction on aldehydes and ketones initially, but you can have any carbonyl. So here we have a proton that's alpha to a carbonyl that has a pK somewhere around 20. We can deprotonate here. Here we have, again, an alpha proton that's next to a carbonyl, but that carbonyl happens to be an ester. That's still acidic. Not quite as acidic as the ketone, but it is still acidic, and we still can deprotonate here. Okay, but carbonyls are not the only groups that impart acidity to the carbon adjacent to it. Okay, the nitro group, the NO2 group, also makes this carbon acidic. In fact, significantly more acidic than having just a carbonyl. And the cyano group is another group that makes alpha carbons acidic, kind of like the same as an ester might. Okay, and let's think about, let's draw those conjugate bases to see if it makes sense to us. This should make sense on why each of these hydrogens is acidic. If we have a ketone and we put an anion here, why would that be an appropriate place to have an anion? Well, because it's next to the carbonyl and it can have resonance. Okay, how about if I had an ester? I'm sorry, I have an ester, have a methoxy group over here instead of just a methyl group. Well, we could still have resonance here, and this is still a resonance stabilized enolate. So you can make the enolate of an ester just like you can for a ketone. Okay, but how about the nitro or the cyano? Well, let's take a look at the structure of the nitro group. So let's imagine deprotonating. So we just lost a proton here, and we now have this anion. When you draw out the nitro group, it looks something like this. And how would that be a stable carbanion? Well, this can have resonance just like a carbonyl can. We have an NO double bond instead of a CO double bond, but just like the carbonyl could, we can use that to delocalize the negative charge and move it to an oxygen atom. And of course, having a negative charge on an oxygen atom means this is a very good resonance form. Okay? Plus you have this positively charged nitrogen pulling electron density and stabilizing inductively. That's why this is even more stable than an enolate and makes that alpha proton so much more acidic. How about a nitrile? Let's imagine this anion and draw out the nitrile. Nitrile, of course, has a CN triple bond. Well, again, we have an allylic negative charge, then the allylic lone pair, so the lone pair can come in and the pi bond can move over. So we can have resonance, puts the negative charge on nitrogen. That's not as good as oxygen, but it's certainly better than carbon, and it's because of this resonance stabilization that it makes it a reasonably acidic proton and something we can deprotonate with a strong base like LDA. So these are enolate-like species. When we say enolate, we mean a carbonyl of some kind, either a ketone or an aldehyde or an ester, but these are enolate-like species as well. Just a quick question, why, there's a big difference here, 5 orders of magnitude less acidic for an ester compared to a ketone. Why do you think that's less acidic? What is there about this conjugate base that's better than this conjugate base? Or why would a ketone be less willing to donate a proton? It must have something to do with this OR group. Well, remember, what effect does this oxygen have to the carbonyl next to it? It is an electron donating effect to that carbonyl. So an ester carbonyl is more electron rich. So that means it does not want to have this negative charge. This negative charge now has to compete with the oxygen's electron donation for this carbonyl, so there's less resonance stabilization that can go on to delocalize that negative charge, okay? So it's because the ester ketone, the ester carbonyl is more electron rich that, that makes it a weaker acid. So just to summarize, the carbonyl, the nitro, the cyano, each of those groups are described as electron withdrawing groups, or EWG for short. And what they all have in common is if you put a negative charge right next door to them, they would be able to stabilize that negative charge by resonance. So that puts these three groups together in a certain category. We're going to see lots of examples actually where the EWG comes into play and imparts a particular reactivity to the groups attached to it. So now that we've taken a look at how to make enolates, what's the mechanism, what kind of bases can we use, what types of alpha protons are going to be acidic, what would we do with an enolate? How are they used? Well, they're carbanions. They're examples of carbons with a negative charge, which makes them good nucleophiles. Anything that's electron rich is going to be a good nucleophile, and so we're going to react it with a variety of electrophiles. So electrophiles are things that are electron poor, things like an alkyl halide. That's an electrophile we've seen. We know that this halogen, chloride, bromide, iodide, pulls electron density from this carbon, making it partially positive. So we can have nucleophiles attack here doing something like an SN2 mechanism, for example, and so an enolate would be an example of that. Okay, or even just Br2 or halide like that. It doesn't have a carbon bearing a leaving group, but it's got a halogen bearing the leaving group. So for that same reason, you could have an SN2 occurring with that. We'll see reactions of enolates with something like Br2. Now a carbonyl has a partial positive, partial minus. So we've seen carbonyl reactivities as electrophiles, and we'll see something like a ketone, aldehyde, ester. Okay, in general, any carbonyl would be a good electrophile, and we'll see enolates react with those. And finally, an epoxide would be a good electrophile as well. Remember, the carbons of the epoxide are partially positive because the oxygen pulls electron density. There's a lot of ring strain involved in that three-membered ring, and so those also readily react with nucleophiles. So let's look at some of these examples. The first one, reaction of an enolate with an alkyl halide, is described as an alkylation reaction. And let's take a look at this reaction sequence. If we were to take cyclohexanone and first treat it with LDA, remember that's lithium diisopropyl amide. Every time we see LDA, we know that we have a base, a strong, bulky base. And what do bases do? They deprotonate. So we look at cyclohexanone and ask, where can we deprotonate? And of course, it's that alpha proton that is going to be acidic. So step one is going to deprotonate the alpha carbon to give us a carbanion. Okay, and what I'm suggesting is that this carbanion now is going to be a very good nucleophile. So in step two, when I react with methyl iodide, which is a good electrophile, what reaction can happen here? I think the nucleophile is going to attack the carbon, kick off the leaving group. That looks like a backside attack, looks like an SN2 mechanism. That's exactly what happens. And I have now installed a methyl group at the alpha carbon. So this is called an alkylation, or an alpha alkylation reaction. And it's this two-step process. We deprotonate, and then we treat it with an alkyl halide. Now, because it's an SN2, remember that backside attack requires minimum steric hindrance. So we have to have an unhindered alkyl halide. A methyl group would be great. Primary would be fine. But as soon as we get to secondary or tertiary, then E2 is going to be preferred because the enolate is still a pretty strong base. Now, as shown here, the enolate is a nucleophile at carbon. In other words, C alkylation, putting the alkyl group on the carbon is preferred rather than O alkylation, okay? And this is important to point out because remember the enolate has two resonance forms. And it doesn't matter which resonance form you draw, you should still be getting the same product. Okay, so let's take a look at the mechanism using the better resonance form, the preferred resonance form. So what we'll do is we'll have our base come in, our LDA come in and deprotonate, but instead of putting the negative charge on this carbon, the more appropriate place to put that negative charge is on the oxygen. So I'm going to draw the enolate like this. Now that's the better resonance form because it has a negative charge on the more electronegative oxygen. In other words, this better represents the actual hybrid of the enolate structure. However, it's very tempting now when you look at this to think when I bring this together with my electrophile, it's very tempting to use the negative charge from oxygen to go and attack. That would be described as O alkylation, where the alkyl group ends up on the oxygen. That does not happen. That does not happen. It is the alpha carbon. It is the alpha carbon. That is the nucleophile in an enolate. No matter how you draw it, it's the alpha carbon. So how do I get this carbon to react? Well, this is what enolates do. The enolate is here. The enolate is a nucleophile. And I'm going to start with the lone pair up on the oxygen. But instead of having that attack the electrophile, it's going to come down and reform the carbonyl. And that's going to push these electrons out. We're going to form this bond here between the alpha carbon and the methyl group. So these two electrons are going to come and attack the carbon, and that's what kicks off the leaving group. So it's the alpha carbon that's nucleophilic and does the SN2. So now when we follow the arrows around, I see that I'm back. My oxygen has two lone pairs. I have my carbonyl back, and attached to that alpha carbon, I have my alkyl group. Okay, this is typically how we're going to be drawing our enolates for the rest of the chapter, and how we can use them. This is not wrong. This is still an acceptable drawing of an enolate. It's just not as good a representation as this one. So we want to get used to using this mechanism. So what else can we do with the alpha carbon? We can also halogenate at the alpha carbon. That reaction is described as alpha halogenation. And here's an example. If I take this ketone, treat it with chlorine and base with water, I can install a chlorine in the alpha position. Now that mechanism is analogous to the one we just saw for alpha alkylation. We deprotonate the alpha carbon, and then we attack the Cl2 to put in the chlorine. Okay, and that we can look at that reaction, but this reaction is not that useful because this product that we formed, if you take a look at that alpha carbon, it turns out that this is now more acidic than your starting alpha carbon. And why is that? Well, we just added a chlorine here. We know chlorine pulls electron density, or any halogen is electronegative, pulls electron density here, so that enhances the acidity here, makes it easier to deprotonate here. So now I'm going to be forming some of this enolate, and I'm going to end up doing adding a second chlorine. So we could have multiple halogenations. So this would not be a very good way to make this 2-chloro 3-pentanone, because it would be hard to stop at this case. Anytime your product is more reactive than your starting material, it's difficult to control those reactions. Okay, in fact, it's so reliable that there's a test called the iodoform test that counts on this overreaction. And it's when you have a methyl ketone. So I have a CH3 here, and attached to a carbonyl, that's called a methyl ketone. If you treat a methyl ketone with iodine and sodium hydroxide, what happens is you end up replacing all three of those protons with iodines by successive alpha halogenations. And that turns this group into somewhat of a leaving group. Now, it's very unusual to have a carbon leaving group, but because that carbon has three iodines on it, all pulling electron density away, it can make it it is a reasonable leaving group. And so hydroxide can add in to the carbonyl now and do a substitution reaction. We can get a CTI, and again, even though we don't normally think of this carbon as a leaving group, it can in fact get kicked out And the product we're going to get, we'll get CI3 minus, which gets protonated to iodoform. And we'll get the carboxylic acid product out here when we're done. And this ends up being a precipitate. This is a yellow precipitate, and this is the test. The iodoform test is when you treat a sample with iodine and sodium hydroxide. If a precipitate forms, then that is a chemical test, a qualitative test, to indicate the presence of a methyl group attached to a carbonyl. So these kind of tests are outdated now that we have such powerful spectroscopic techniques like NMR, where you can really see a methyl ketone a lot more less ambiguously. But this still has some historical notes, and you'll often see this reaction still in textbooks. So with a base promoted reaction, we expect to have multiple halogenations. If we want to do a single halogenation, that's possible, but what we're going to do is we're going to use acid promoted reaction conditions instead. So in this case, if we used Br2 but with acetic acid now instead of a base, here we see a carboxylic acid, so we recognize that these are acidic conditions. It is possible to get a single halogen in here with good yield. Okay, but because our conditions now are acid catalyzed rather than base catalyzed, we can't use the enolate, we're going to use the enol instead. So the first two steps are going to be making the enol. Remember, we already looked at that mechanism. It might help to think about what the enol structure looks like. The enol has, instead of a carbonyl, it has an OH, and then it also has the double bond between what used to be the carbonyl carbon and the alpha carbon. So that's the enol. And what are the two steps to get there? Well, first we need to protonate. We'll just abbreviate our acetic acid as HA. So step one is protonate. And then step two, I need to deprotonate. This is our tautomerization mechanism. It's just a series of protonations and deprotonations. I'm going to take this alpha carbon. I'll use the A minus that I just had. So this is catalytic in acid. Because I use the acid in the first step and I get it back in the second step, I'm going to form the pi bond and move the pi bond. So two steps. We should always be able to form an enol. And an enol now is a nucleophile just like an enolate. It's not as easy to see because we don't have a negative charge, but it is nucleophilic, and it's nucleophilic at the alpha carbon just like the enolate was. So if we bring in Br2 as our electrophile, notice it has that leaving group attached to the bromine. How are we going to get these two together? Well, we're going to react the enol just like we did the enolate. What we're going to do is we're going to start up on this oxygen, this lone pair. We're going to form the carbonyl, and that's going to kick the pi bond out, right? We're forming this bond between the alpha carbon and the bromine and kick off our leaving group. So that installs a bromine at the alpha carbon. This gives me an oxygen. I still have the hydrogen on here. What else do I have? I have the pi bond, and I have just one lone pair left and a positive charge. So I'm very close to my product, right? What do I have to do to get to my product? I simply have to deprotonate the carbonyl. We can bring A minus back in, or we could use the Br minus that we just formed, and we can deprotonate. So as we'll see is common in these reactions, the acid catalyzed reaction is going to be more steps than the base one, and we'll be using an enol as our nucleophile instead of an enolate. But this would be a way that we effectively can do an alpha halogenation on a ketone or an aldehyde. So we've seen how to add a halide to the alpha carbon. We've seen how to add an alkyl group to the alpha carbon. What other electrophiles are there? Well, the carbonyl, of course, is a big electrophile, and we'll study that reaction next. We're going to be spending quite a bit of time actually on that reaction. It's known as the aldol condensation, and it's the reaction of two equivalents of a carbonyl-containing compound, an aldehyde or a ketone, We'll take a look at an example where it uses base, but it can also be acid catalyzed. We'll see both mechanisms here. And the product looks like this. Now, we use 2 equivalents of the aldehyde, and here's one of them, and then here's the other one. So it's like we had our, if we drew the second acetaldehyde molecule down here, you can see here's the reaction that's happening. We're forming a bond between this alpha carbon and this carbonyl carbon. Okay, and we'll take a look at that mechanism next. Now this product has both an aldehyde component and an alcohol component. So this is described as an aldol product because it has an aldehyde and has an alcohol. So this is actually one of the few cases in organic chemistry where this is not named after Professor Aldol. This is not a name reaction that's capitalized. It's simply described as an aldol because that's what the product might look like. Okay, and we'll also see that if you heat an aldol product, you can cause it to lose water. So this aldol product will react further upon addition of heat. It readily loses water to form this carbon-carbon double bond. So we'll look at both of those mechanisms. How do we get to this aldol product, and then how does that aldol product lose water? Okay, let's look at the base catalyzed mechanism first. And when we're in base, we're going to deprotonate first. Let's ask where would be a good place to deprotonate. Certainly it's going to be the alpha carbon, because that's the theme for this unit. And so this is not an alpha carbon. This is not an alpha proton. This is attached directly to the carbonyl. That's not at all acidic. But here's my alpha carbon. Here's an alpha proton. Let's change that to a CH2 so we can see one of those hydrogens. And absolutely, that's going to be our first step, is to deprotonate that alpha carbon to form an enolate. Now, every one of these steps is reversible, so we'll use our equilibrium arrows here to go from one to the other. Okay, so my first step is to make an enolate. And what kind of reactivity do we expect for an enolate? Well, it is a nucleophile, so we need to look around for an electrophile. Okay, and this is where it becomes important, the choice of base that we used. We only used hydroxide. We didn't use LDA in this case. We just used hydroxide. Hydroxide is a weaker base, so it has taken some molecules of this aldehyde starting material and made the enolate. But by and large, most of this aldehyde is still the aldehyde. So the aldehyde is still present. And therefore, it can serve as our electrophile. The carbonyl can be our electrophile. So we let our enolate do its thing, form the pi bond, form the carbonyl, kick the pi bond out, and attack the carbonyl. And then what happens when a nucleophile attacks the carbonyl? We break the pi bond and move those electrons up. So let's redraw our enolate part here. We now have our carbonyl back. We have a new bond from this carbon to this carbon. Right, this carbon is this carbon. Now what do I have on this carbon? I have an H and a C. I have a hydrogen and a methyl, and I have a single bond O minus. So that is a nucleophile attacking an electrophile. Not quite done yet. We have an O minus. How can we get rid of an O minus? All we need to do is protonate. So we can bring, we just used water. We formed water in this first step when hydroxide acted as a base. So we could use water as our acid. And we can protonate the O minus. And we have our aldol product. There's our aldol product. Notice it has a new carbon-carbon bond because we had a carbon nucleophile attacking a carbon electrophile. So here's the new carbon-carbon bond in the aldol product. That's going to be important to us to identify when we try and do synthesis problems. Okay, and overall then in base, it's going to be a three-step mechanism. First, we deprotonate, and then we had attack of the enolate onto the carbonyl, and then we protonate. Deprotonate, attack, protonate. We're going to see that pattern again and again and again for base catalyzed mechanisms. Okay, so a summary then. An aldol, what does it mean to be an aldol reaction? It forms a new carbon-carbon bond between the alpha carbon of one carbonyl compound, in this case a ketone or an aldehyde, and the carbonyl carbon of another. Between the alpha carbon and the carbonyl carbon, we describe that reaction as the aldol reaction. Now we said that this aldol product can lose water, so let's draw the aldol product we have so far. And we said that this now can undergo loss of water, and that mechanism is also a two-step mechanism. It's described as a beta elimination, okay, and it starts, the first step is going to be to deprotonate. So I'm going to take that hydroxide again, and I'm going to deprotonate the alpha carbon, so let's just make that a CH. We're going to deprotonate the alpha carbon and make an enolate. And now typically after we've made an enolate, that enolate that we've used thus far in mechanisms, that enolate has always formed this pi bond and formed the carbonyl and kicked this pi bond out to some external electrophile. But in this case, what we have is a leaving group that's in the beta position. Remember, the alpha position is the first carbon next to the carbonyl. The beta position is the next one over. And hydroxide can act as a leaving group. So when you have a leaving group in the beta position, that enolate will reform the carbonyl, shift this pi bond down, and kick the leaving group off. So we're going to deprotonate as our first step, and step 2, we're going to eject the beta leaving group. And when we do those 3 arrows, the product we get is the aldol product that we're expecting, the carbon-carbon double bond in between the alpha and the beta carbon. So this is our mechanism. This step here kind of looks like collapse of a CTI a little bit. Remember, collapse of a CTI is when we had an O- kick down, and on the same carbon it had an OH, it would kick off the OH. This is an extended system, but it's still the O- kicking down and forcing the OH off. Okay, now think about, we just lost hydroxide here. That's not a typical leaving group, but we have seen it before for collapse of a CTI, so that's acceptable. And now we're seeing that because this mechanism is similar, it's also acceptable for a beta elimination mechanism. You can lose hydroxide as a leaving group. Okay, and remember, the reason for both of these, the reason that it's okay is that your driving force is that your formation of the carbonyl. In both of those mechanisms, what's pushing the hydroxide out is an O-, which is forming a carbonyl at that same time. So because I'm forming this carbonyl, it's okay to lose hydroxide as a leaving group. Okay, just a quick note of caution that this loss of water, this mechanism is not an E2 mechanism. Okay, it's very tempting. Here I've redrawn it. If I wanted to go from this aldol product and eliminate water, what's very tempting is that I just use my base to deprotonate, and instead of using it to form an enolate like I need to, I think, well, let's just form this pi bond and kick out the leaving group. Wouldn't that be a fast, easy mechanism? Shouldn't that be better? Okay, that would be an E2 when you have a single-step elimination mechanism. That's described as E2. Okay, but that does not happen. There's no way we could do an E2 because hydroxide is not an acceptable leaving group for such a mechanism. You have to have a traditional leaving group like bromide, chloride, iodide, tosylate, something like that in order to enable this. The only reason this elimination can take place is because of this carbonyl, because you have this resonance stabilized enolate intermediate, and so it's critical and must be used as part of your mechanism. Okay, so just a reminder not to do a single step elimination here of water, but to do a 2-step beta elimination. Okay, so let's summarize the aldol. An aldol is what we have when we have an aldehyde or ketone. We're going to treat it with either base or acid. The aldehyde, the ketone in this case, is going to serve both as the nucleophile. The alpha carbon is going to be the nucleophile, and it's going to serve as the electrophile. The carbonyl of the second molecule is going to be the electrophile. So there's the bond we're forming. So we form a new carbon-carbon bond between the alpha carbon of one and the carbonyl carbon of the other. Okay, so the product we get could be described as a beta hydroxy ketone. Right? Not in the alpha position, but in the beta position where it's going to have this hydroxy group. And then if we heat this, we can lose water, and so now we form a double bond between the alpha carbon and the beta carbon. So this structure is described as an alpha-beta unsaturated ketone, because we have a point of unsaturation. We have a double bond between the alpha carbon and the beta carbon. So when we do an aldol, we can get you can kind of choose which product we want to draw. It's either the beta hydroxy ketone, or sometimes it's an alpha beta unsaturated ketone. Very often the trigger on whether or not you're going to lose water will be the addition of heat. Okay, sometimes this is spontaneous because this dehydration is a relatively easy one. Okay, let's think about why that is. Typically when we dehydrate an alcohol, we need strong conditions: sulfuric acid, phosphoric acid, heat. It's very hard to dehydrate an alcohol. This one happens very, very easily. You don't need a strong acid. You could even do it in base, and you just need to warm it up a little. In many cases, it's very, very facile. Okay, but think about your final product. You're not just forming an ordinary carbonyl. It's not just an ordinary alcohol. It's a beta hydroxy alcohol. It's beta to a carbonyl, and so this resulting double bond is now going to be conjugated with the initial carbonyl. This is a conjugated system, and that conjugation, when you have a double bond right next to another double bond, means you have resonance, and it's a very stable structure. So that's why aldol products are very likely to lose water and go to an alpha beta unsaturated carbonyl. Okay, so far we took a look at the base catalyzed mechanism. We'll look at the acid next, but let's draw some comparisons. In the base catalyzed mechanism, all the species were either neutral or they had a negative charge. The nucleophile we used was the enolate. The electrophile we used was the ketone, the carbonyl. Okay, now how is that going to change for an acid catalyzed mechanism? Now, an acid catalyzed mechanism, you can't have a strongly basic species like an enolate. You need to have either neutral compounds or positive charges. We're not going to have any O- in an acid. So instead of an enolate, what species can we use that would still be nucleophilic? How about if we protonated that to make it an OH, what would that be called? That's the enol. And that is going to be the nucleophilic species in the acid catalyzed. We also can't have a neutral carbonyl, because if you attack a neutral carbonyl, that forms an O-. Can't have an O- in an acid catalyzed mechanism. So what we're going to do is we're also going to protonate the carbonyl, and it will be a protonated carbonyl that gets attacked. So it turns out that this mechanism is going to be a little longer in order to accommodate these species, but let's take a look at that. So we said we have to make an enol. Those will be our first two steps of the mechanism then. We'll start with we're doing acetone in this case, and we have some acid present. So to make an enol, first we protonate. And then the second step to make the enol is deprotonate. So we take this alpha proton with A-, and we have an enol. So that has to be our first two steps, is to make the enol. Now I have my nucleophile. What electrophile is it going to react with? What we just saw on the previous slide, it's not going to react with a neutral carbonyl, it needs to react with a protonated carbonyl. We just showed the mechanism on how to form the protonated carbonyl, so we can use that again. But this is going to be our electrophile. And what is the bond that we're going to be forming? It's going to be between this alpha carbon and this carbonyl carbon. So our mechanism to get there is our enol starts at the lone pair on the oxygen, forms the carbonyl, and that's what kicks the pi bond out, kicks those electrons out. Those attack the carbonyl of the electrophile and break the pi bond. That's the key step in any aldol, is when the alpha carbon attacks the carbonyl carbon. So let's see where this brings us. Let's redraw the enol. Now has a carbonyl, still has the proton up here. And we just formed the new bond between the alpha carbon of one and the carbonyl carbon of the other. And what does this carbon have on it? It still has the two methyl groups, and it has a single bond OH. And what do we have to do to finish this up? Looks like we just have to deprotonate. So we'll bring A minus back in here. And we're done. There's our aldehyde. So once we made our enol, then we protonated the carbonyl, we attacked the carbonyl, and we deprotonated the carbonyl. Okay, but it's going to be a little longer mechanism to get where we want to go. Notice overall, there's no O minus charges in the acid. Everything is positively charged or neutral. That's going to be consistent with any acid catalyzed mechanism. Now let's think about losing water from that aldol product to form the alpha beta unsaturated ketone. We described that mechanism as a beta elimination mechanism. We saw in base it was just two steps. The first step was we deprotonated to make the enolate. And then the second step was that enolate kicked down, and kicked out the leaving group. So reject the beta leaving group. Now how do we have to adjust that? Who was the beta leaving group? It was hydroxide in the base catalyzed. So how are we going to adjust this for the acid catalyzed version? We can't have an enolate, so instead we're going to make the enol. Okay, and what do you think about hydroxide? Do you think that would be an acceptable leaving group in acidic conditions? No way, much too strong of a base. So what would be a leaving group that would be okay to have around in an acidic solution? We would have to lose water. Okay, so with that in mind, let's think about our mechanism. Let's give it a try. So we're going to start with our aldol product. We want to lose water from this. So the first thing we need to do is we need to convert this to the enol. How do we make the enol? Two-step tautomerization mechanism, two steps. First we protonate. That tautomerization practice is really going to pay off when you get to these more complex mechanisms, so that hopefully this part will be somewhat automatic. Protonate at the carbonyl and then deprotonate at the alpha carbon. So that's the first thing we have to accomplish, is we have to make the enol. Okay, and now we need to get rid of our beta leaving group, but it's not a good leaving group right now. If this kicked down and kicked off the leaving group, it would be hydroxide leaving. So how do we make it a better leaving group? We need to protonate. And so now it's going to look like water when it leaves. Looks like water right now as it's attached. This is a good leaving group in acid. So when we said that hydroxide is an okay leaving group for collapse of a CTI or for beta elimination, that's true, but that assumes you're looking at a base catalyzed mechanism because you have hydroxide. In this case, we need water as our leaving group. So now we're ready to do our beta elimination and eject that beta leaving group. Same idea as with the enolate though. We're going to start up here in the lone pair on this oxygen, form the carbonyl. That's what pushes this pi bond down. That's what kicks our leaving group off, right? We just lost water. And now we track our product, see where we are. This now is an O plus up here, so we're this close again. We just have one proton to go. All we need to do is deprotonate. We could bring A minus back in. A minus, of course, that's the only negative charge we can have in an acid catalyzed mechanism. A minus represents some very stable conjugate base of a strong acid, like sulfuric acid conjugate base, let's say. Okay, so that would be an okay thing to have in acidic conditions. So final deprotonation, and we've done our elimination. So again, it was just 2 steps in base and several steps in acid, but practice with the base, get used to that, understand the logic, and be able to talk yourself through the mechanism and know where to go so that you can make those adjustments and make it work for acid. So again, all positive charges or neutral species. Now, in all the cases we've looked at so far, aldol has always been a self-aldol, meaning one molecule of a ketone has reacted with the exact same molecule of a ketone, exact same structure of another molecule of a ketone. Okay, when we have 2 different ketones or aldehydes coming together, this is something that can be reasonable if only one of the compounds has alpha protons. So, for example, if we bring it together acetone and benzaldehyde with base, sodium hydroxide and water, we think about who could be the nucleophile, who could be the electrophile. Well, we know we have a base here, so we can deprotonate, and we're going to look to our alpha carbons to deprotonate. Well, acetone certainly has an alpha carbon, so this one, when we deprotonated, that would be our nucleophile. We have one nucleophile here, but how about benzaldehyde? There's no alpha protons on the benzene ring, and this hydrogen is not alpha, so this has no alpha hydrogens, so that means this cannot be a nucleophile in any way. It has to be an electrophile. So we only have one nucleophile. How about looking for electrophiles? Well, both of these structures have carbonyls, so you might think they both could be the electrophile in the reaction. Okay. However, we have a ketone and an aldehyde, and the aldehyde is the better electrophile. Now let's just take a quick look at why that is. Okay, well, remember, alkyl groups donate electron density. So when we look at a ketone, we know that these carbons are going to be adding electron density to the carbonyl. That makes the ketone more electron rich. Okay, is that good for an electrophile? That is not good for an electrophile. Okay, this is more electron rich, and so this is a poorer electrophile, and the aldehyde is the better electrophile because this only has one alkyl group donating. This has a larger partial positive. So comparing an aldehyde and a ketone, an aldehyde is going to win in terms of electrophilicity and reactivity. And so comparing acetone and benzaldehyde, benzaldehyde is a better electrophile. So we have one electrophile, we have one nucleophile, which means we can expect to get one major aldol product. And what would that look like? Well, we could start by drawing our acetone. We know we're going to form a new bond between this alpha carbon as our nucleophile. And where is it going to attack? It's going to attack this benzaldehyde carbonyl. So this used to be a CH3. It is now a CH2 because we deprotonated there, and that's how we have room for this bond. And then when we're all done, what do we have on this carbon? We have a phenyl, we have a hydrogen, and we have an OH. It would be an O minus, but we would protonate it at some point. So we get this beta hydroxy ketone. This would be our major product. However, this probably would lose water spontaneously. We wouldn't really have to warm this up, probably. Just having it at room temperature would be enough for this to lose water. In this case, it's very likely that you would get this as your major product. Okay, and let's think about this particular example. Why is it in this case that it would be very difficult to isolate this alcohol, very difficult to not have it undergo this dehydration step, this beta elimination step? Well, that's because we have this double bond not only is in conjugation with the carbonyl like it always is in an aldol, but we also have this benzene ring right here. So this is conjugated with the benzene ring pi bonds, and that makes this pi system, an extended conjugated pi system, very, very stable. So in the case with benzaldehyde, it's very common to seemingly spontaneously lose water and go straight to the alpha-beta unsaturated carbonyl, even though you haven't seen the addition of heat explicitly. Now, what if I wanted to do a mixed aldol between two ketones or two aldehydes, two groups that have similar reactivities? Well, we could exert control there. We wouldn't just want to mix those two together in the presence of base, because then you can get all sorts of possible products out. You have two possible nucleophiles, you have two possible electrophiles. So in a mixed aldol like that, you might have up to four possible products. But the way you could exert control is, instead of just mixing everything together, you could do it stepwise by using something like LDA. Remember, LDA is our strong base. And so if we started out with just a single ketone and treat it with LDA, we would expect that ketone to be deprotonated. Now, this is an interesting case because we have two different alpha protons in this case. How would we know which one is the major site of deprotonation? Well, remember lithium diisopropylamide, it had those two isopropyl groups. It's a very bulky base. LDA prefers to attack the less hindered alpha carbon, and therefore alpha proton. So it has to do with sterics, it has to do with kinetics. It goes to the less hindered side. So this is going to deprotonate to give the following enolate. Sorry, this is a CH2. So we have just one nucleophile. We have this enolate being formed. Remember, the reason we use LDA, we use a full equivalent of LDA, so this gets completely converted to this enolate. Okay, and now, after the enolate's formed, now we add in the second carbonyl. We have just one electrophile, so there's really just one major product that can occur. What's the bond that we're going to form? The electrophile is reactive at the carbonyl carbon. The enolate is reactive at the alpha carbon, and so we expect the enolate to attack the carbonyl. And so what is our product going to look like after workup? We're going to form a new bond to the alpha carbon, like we would in any aldol. This carbon is part of the six-membered ring. And then on this carbon, we also have a single bond O minus, which then gets protonated upon workup. Now we would do a separate workup when our reaction's all done, and we get this beta hydroxy carbonyl. Now, I want to point out just some steps here, some common mistakes. It's very common to draw as the product of this product. Now, what would be the problem with drawing this product? You've attached the carbonyl carbon to the carbonyl carbon. Something's missing here. Okay, you have an alpha hydroxycarbonyl. That's not the product you should be getting. It should be a beta hydroxycarbonyl. So especially when it comes to line drawings, very easy to lose carbons when you're drawing your zigs and zags. So make sure you explicitly show your alpha carbon, that was your nucleophile. There's a new bond to your beta carbon, which was your electrophile, the carbonyl carbon, and that way you won't make mistakes of accidentally losing carbons when you're dealing with line drawings. Let's see if we could take one of these problems and do it as a retrosynthesis. If we're given this starting material, this target molecule, rather, and asked to synthesize it, how could we do that? Can we predict what reagents we need for the aldol to give this target molecule? Remember, a retrosynthetic arrow asks, what starting materials do I need? How could I create this target molecule? Well, it looks like an aldol product. Even if it doesn't give us that clue, it looks like an aldol product because between the alpha and the beta carbon, we have a double bond. This is an alpha-beta unsaturated carbonyl. Ketone in this case. And that is the type of functional group pattern we would get if we did an aldol reaction. So it's possible to just kind of disconnect the bonds that we know that are being formed, but I think maybe an easier step backward would be to say, okay, well, remember I got this double bond because I lost water from the beta hydroxy ketone. So maybe you can kind of add water back in. Let's abbreviate this as just a phenyl group. Let's add water back in so that we add the hydrogen and we add OH. We already had hydrogens here, so we can leave those in if we want so we don't get too confused. Let's add water back in to go back to the beta hydroxy ketone, because this is also a pattern that we could get from the aldol reaction, but it's a little easier to grab onto this one because we have some more interesting functional groups. Okay, the key disconnection we make, remember what is an aldol? It's the reaction of an alpha carbon to a carbonyl carbon. So this is the key disconnection that we make in an aldol. It's between the alpha and the beta carbons. So this carbon, remember, one of these carbons was a nucleophile, one of them was an electrophile. That's how they were able to come together to make this product. The alpha carbon, of course, was the nucleophile. This alpha carbon was the nucleophile. In other words, that was the enolate in the mechanism. And that means that this carbon was my electrophile. What electrophile could I have that after it gets attacked, we end up with an alcohol at that carbon? It was a carbonyl. If I had a carbonyl here and an enolate attacked it, it would break the pi bond and I would get an alcohol there. So that's the logic we can use when we do this disconnection then. We end up with just a phenyl and a 1-carbon aldehyde. Looks like benzaldehyde again is involved in this. That would be our electrophile. And what would our nucleophile be? It would be a phenyl group with a carbonyl and then a CH3. So if I had acetophenone and benzaldehyde, I could actually just mix these two because this is similar to the mixed aldol we just looked at. Because this is a ketone and this is an aldehyde, I could just mix these two together in the presence of base, sodium hydroxide and water, or methoxide and methanol, something like that, and a little heat to afford the dehydration. These actually would come together to form this single product as our target molecule. We'd expect to get this as our major aldol. We wouldn't have to bother first treating this as LDA and then adding the benzaldehyde separately. Okay, but this would be a good process by which we could come up with the starting materials required for an aldol synthesis. Next, let's take a look at a reaction called the Claisen condensation. This is very much related to the aldol condensation. In fact, it is an aldol reaction, but instead of using a ketone or an aldehyde, we're going to be using an ester instead, and we call that a Claisen. So let's look at an example of it and see where it takes us. Let's say we have this ester, and we react it with ethoxide, sodium ethoxide, and ethanol. This is a base. Anytime you see hydroxide, alkoxide, you know it's a base. And then after that, we're going to do some mild workup. Let's see where it brings us rather than looking at the product first. So what do you think the first step will be of this mechanism? We have a base, so let's deprotonate something. Where do we deprotonate? Alpha carbon. Alpha carbon, alpha carbon, alpha carbon. That's the whole theme of this lesson. So I'm going to look, remember these carbons are not attached to the carbonyl. Those are not alpha carbons, but this one is. So I could use ethoxide as my base, and I could deprotonate the alpha carbon. This is done reversibly because ethoxide is not LDA. It doesn't do so in just one direction. But I will get out some of this enolate. Let's just abbreviate this. This is an ethyl group here, so we could abbreviate it OET. That would save us a little time drawing. Okay, so deprotonate to form an enolate. That's a good idea. And what kind of reactivity does an enolate have? We know that's a nucleophile. So let's look around for potential electrophiles. Well, remember, because we use this weaker base ethoxide, we still have most of this ethyl acetate is still as the ester form, so that's still around. So we can bring in another molecule of the ethyl acetate as our electrophile. So see how it's just like an aldol? we have an enolate of a carbonyl-containing compound attacking a non-deprotonated copy of itself. So our enolate does its thing, reform the carbonyl, break the pi bond, and then what happens when you attack a carbonyl? Always, always, always the same. Break the pi bond and move it up on oxygen. So let's draw this product over here. Let's draw our enolate again. It now has a carbonyl. Single bond to the alpha carbon, new carbon-carbon bond here. Very good. And then we have what's on this carbon? We have a CH3. We have an O minus. And we have an O ethoxy. We have an O ethyl. Okay, now if this were an aldol reaction, if we were using aldehydes and ketones, our reaction would be done right now. Essentially almost done. We deprotonated, we attack, and then all we would do is reprotonate. We'd have our beta hydroxy ketone product. Okay. However, when you're dealing with an ester, the path, it takes a different path, because what happens when a nucleophile attacks an ester? You now have an O minus on the same carbon as a leaving group. We call this a CTI, a charged tetrahedral intermediate. So this is not a stable intermediate. This is not just sit around and wait for a reaction to something to come and protonate it. What happens to a CTI? We use two arrows and we collapse that CTI. Lone pair comes down, leaving group gets kicked off. And so our product ends up being this. We kick off ethoxide. Right? What happens with esters when they get attacked by nucleophiles? We get addition, elimination. We get a substitution at that carbonyl. So taking the place of this ester, of this ethoxy group, is going to be the enolate group. Okay, and it looks like our reaction is done here. Because we're at a nice, stable, neutral, happy product, and this is the ultimate product that we will be isolating. However, in the reaction conditions, this product is not stable because our reaction conditions are basic. And where do you see about this product that makes it want to react with base? We have an active methylene here. We have an active methylene that has two EWGs, two electron withdrawing groups. It has an ester and a ketone attached to it. That makes it very acidic, and because we are in basic conditions, we're going to deprotonate this, and we could draw it if you'd like. We could deprotonate the alpha carbon. Okay, to make this stabilized enolate, of course, this has lots of resonance, so this is very, very stable. And in fact, this last step, this final deprotonation, is the driving force for the Claisen. If we did not have this last step, if for some reason you didn't have a hydrogen here and you couldn't deprotonate, the Claisen actually wouldn't go. The retroclaisen would happen instead. So it's because this final step is essentially irreversible. This is such an acidic proton that we get this as our final product. Okay, so that's what happens after step 1, and now you can see perhaps why we need this step 2. We need to have an acidic workup to reprotonate this enolate that's formed as the final product. And that's how we can get the product that we kind of imagined we were going to get. We can go back to this neutral intermediate that we had for a fleeting instant, and we come back to our actual Claisen product. So how do we describe the Claisen product? It is described as a beta keto ester. So we've added a new group. We've added a new bond to our alpha carbon, and the group that we've added is another carbonyl because we had addition elimination at that ester group. We had a substitution there, so that regenerates the carbonyl in the beta position. So we get a beta keto ester when we do a Claisen condensation. Let's take a look at an example, see if we can predict the product here. Okay, we have in this case, we have a methyl ester. So that's why we're using sodium methoxide and methanol. Remember, anytime we want to have a base around an ester, we want to use that matching base. And so what do you think would happen here? Well, I think this base is going to deprotonate our alpha carbon. Where do we have an alpha proton? Right here. So I think we're going to have this anion as our nucleophile. Just see if we could do a little work here without going through a complete mechanism. Let's see if we could come up with the product. And what is that going to react with? Well, there's no other ingredients thrown in here, so this is going to just be a self-Claisen condensation. We're going to have another molecule of our ester. We can draw the carbonyl down here if you'd like, so it's a little easier for it to attack. So we'll bring a second structure in here, and that's our electrophile, our key bond then. Just like the aldol, alpha carbon of one to the carbonyl carbon of the next. But this is going to attack the carbon and break the carbonyl pi bond. But then what's going to happen next? That O- in the following step is going to reform the carbonyl and kick out the ester. Okay, so it's not an SN2 mechanism. You don't want to just bring the arrow in and show it kicking out. That implies a backside attack. But even if you want to do some of this work in your head, you can imagine it going up into the carbonyl and then coming back down out of the carbonyl and kicking off the leaving group. Okay, and that's what it does affect the substitution. And after our aqueous workup or mild workup, we'll be able to get to our neutral product. So can we draw our product, you think? Well, let's redraw this enolate part. CH3, CH2, CH, and then our ester group. And so what we did was we had to take off one of those alpha protons, so we'd have this room here. This is our new carbon-carbon bond, just a little reminder, just like we have in the aldol. And then what is that going to be attached to? That's going to be attached to this carbonyl, which has a propyl group attached to that, CH2, CH2, CH3. And does that kind of look like the product we would expect? We get not alpha but beta. We have a beta keto ester. It's exactly the kind of product we get from a Claisen condensation. Alpha carbon of one, carbonyl carbon of the other. So if you can see its relationship to the analogous aldol, that's really going to help you work through the Claisen when you need to. Let's take a look at one last example. What if we had this diester, and it's a diethyl ester, and we treat it with sodium methoxide, and we just saw what was going to happen. What product can you get? Okay, well, anytime you're reacting something with base, that means we're going to lose a proton, we're going to deprotonate somewhere, and we're going to lose what kind of proton? We're going to lose an alpha proton. We're going to deprotonate the alpha carbon. So this is a symmetrical molecule. Doesn't matter which side we deprotonate. Let's deprotonate over here. We could do that. Okay, there's our alpha carbon. That's our nucleophile. And now, rather than having a second molecule that we can attack, because this has two functional groups, let's see if possibly we can get an intramolecular reaction to take place. Do we have any electrophile internally that's appropriately the appropriate distance away? So let's check. If this is our first carbon, this is 1, 2, 3, 4, 5 atoms away from a carbonyl, which is electrophilic. So would forming a 5-membered ring be a favorable ring to form? Absolutely. 5- and 6-membered rings are the ones that we're always going to be looking for. So what we could do is we can draw a nice 5-membered ring. 1, 2, 3, 4, 5, and number it 1, 2, 3, 4, 5, and then just add in our groups on what's missing. So on carbon 1, what do we have? Attached to that is where we have our ethyl ester, because carbon 1 was the alpha carbon, so it should be alpha to a carbonyl. And then we had a CH2, a CH2, CH2, and then carbon 5, what has what? It has the new bond to carbon 1, of course. Here we can show it as the bond that we're imagining forming. So it has the new bond to carbon 1. And what else does carbon 5 have? It has an O ethyl and it has an O minus. So that's what we would get as one of our intermediates after we deprotonated and attacked. All right, we can imagine this attacking and breaking the pi bond up. And where do we go from here? Well, this looks like a charged tetrahedral intermediate. And so we're going to have this collapse with our 2 arrows. Our O minus comes down, kicks off our leaving group. And we end up forming a ring that still has that same pattern of a beta keto ester that we expect for a Claisen. An intramolecular Claisen condensation has its own name. It's called a Dieckmann reaction. But it's the same exact sort of reaction. Aldol reactions can happen intramolecularly as well to form rings. And Dieckmann is when we have diester cyclizing to do an aldol type condensation. So this wraps it up for part 1 of our enols and enolates discussion, and we'll continue the discussion looking at some different types of species, some different types of electrophiles that enols and enolates can react with next. Thanks for visiting educator.com.